Hello students, in previous lectures we have studied about the VI characteristic of NMOS, PMOS and various relations of current and voltage across the transistor terminals. So, let us solve some numerical examples by using those relations. So, I have written example. Consider NMOS transistor fabricated with L. So, length of the channel is given as 0.16 micrometer and width of the channel is 1.5 micrometer. Process conduction parameter, that is Kn dash, is given 380 microampere per volt square, and threshold voltage Vtn is 0.6 volt, okay, as it is NMOS transistor, N-channel enhancement MOSFET. Find VDS when MOSFET is in saturation. A condition is given, the transistor is in saturation and the drain current is 110 microampere. Now, there are two equations mentioned in the books. So, first equation is ID is equal to Kn VGS minus Vtn whole square. So, this is the drain current when transistor is in saturation. One more equation is mentioned in some books. ID is equal to half Kn VGS minus Vtn square. So, which one we should use? Okay. So, this factor half Kn depends upon how we are finding the Kn. What are the parameters given? Length and the width. We have Kn is equal to, so it is Kn is equal to Kn dash, so it is ratio of width and L. We are using this one to find this, then we have to take half in the equation of ID, and if we are taking half here, then no need to take half in the equation of drain current. So, that is one thing you should remember. See, Kn dash is the process conduction parameter and Kn is the conduction parameter. Already we have discussed about this. So, let us find Kn. Kn is not given here and Kn dash is mentioned. By using this relation we can find this as, so Kn dash is 380 microampere per volt square into width or L. Width is 1.5 micrometer and length of the channel is 0.16 micrometer. So, this gets cancelled, remaining is 380 microampere per volt square. It is 1.5 divided by 0.16. So, it is around, I have calculated already using calculator. So, it is around 3562.5 micrometer per volt square, sorry, microampere per volt square. So, if we cancel this decimal, so it is around, so 3.5 milliampere per volt square. So, it is our Kn. So, here we have not used half Kn dash. So, we have to take half in the equation of drain current. So, it is drain current when NMOS is in saturation. So ID is equal to, so here I am taking half because we have not taken half in calculation of Kn. Therefore, we are taking half here. So it is half Kn to Vgs minus Vtn square. Okay. So what is this voltage? It is the overdrive voltage of transistor. Transistor is in on condition and the voltage on gate is Vgs minus Vtn. So what should the voltage to maintain transistor in saturation region? The voltage on drain should be greater than this voltage. At that time the transistor will be in saturation. We have to find that voltage. We have to find the difference voltage Vgs minus Vtn. If you put all the given things, so it is half and drain current is given, so it is 110 microampere. Half Kn, we have Kn at, it is 3.5 microampere per volt square, sorry, it is milliampere per volt square into Vgs minus Vtn whole square. Okay. So if you simplify this, we will get, so it is 110 microampere, so it is multiplied by 2 and divided by 3.5 milliampere per volt square. Okay. And this is Vgs minus Vtn whole square. So it will be around, so it is, if you use calculator you will get Vgs minus Vtn whole square is equal to 0.06285. So it is whole square. So here, so if we take square root, we will get Vgs minus Vtn is equal to 0.25 volt. So this is the overdrive voltage. Now what is the voltage we have to maintain on drain? So the voltage on drain should be greater than this voltage. So VDS saturation should be greater than or equal to Vgs minus Vtn. So it is around more than 0.25 volt. Okay. When this voltage is maintained on drain, the NMOS will be in saturation, and this is the VDS saturation voltage higher than 0.25 volt. Let us solve the next example. This example is on p-channel MOSFET, that is PMOS. Process conduction parameter is given, conduction parameter is given, Kp is 0.2 milliampere per volt square, and it's a threshold voltage of PMOS. So it is negative. VTP is minus 0.60 volt. And ID DC current is 0.80 milliampere. What should be voltage on drain to operate transistor in saturation region? Okay. So it is a typical example and somewhat complicated as it is p-channel MOSFET. First of all, we should draw the diagram so that we can understand the relations between gate and drain voltages. So it is the PMOS P plus P plus, and we have oxide layer here and metal layer, and here we have channel as it is N type substrate. Okay. The voltage on source and gate. So gate voltage is negative with respect to source. So source is at positive in PMOS. So it is plus and minus. We are keeping notation simple here. So it is plus and minus. So this voltage is VSG. Okay. So S is before G. It means S is positive with respect to gate. That is the major difference between NMOS and PMOS. And the next DC voltage between source and drain. Here also there is a change. It is VSD, not VDS. In VDS, drain is positive with respect to source, means source is negative. Here it is VSD. See the label. So VSD means again source is at positive potential. So this voltage is VSD. So every time the source is positive. Because of that, the direction of current is from source to drain. Okay, exactly opposite to the direction in NMOS. The drain current flows from drain to source. Here PMOS current flows from source to drain. It is the direction of movement of holes, as holes are moving from source to drain. Okay. Now, what is the equation for PMOS in saturation? So we have ID is equal to, directly we can take Kp here, no need to take half because already conduction parameter is mentioned. No need to find using the formula Kp is equal to half Kp dash W by L. If Kp dash is given, width is given, length of given, okay, then we can use this relation to find the conduction parameter by using process conduction parameter. Okay. But all these things are not mentioned. Directly Kp is given, conduction parameter is mentioned. So because of that we are using this equation. See Kp, so it is VGS, VSG plus VTP. So here for PMOS it is plus VSG plus VTP. Let us put the given quantities. ID is given, so it is 0.8, or we can simplify this equation. Okay, we have to find VSG so that we can find the voltage on drain by using this relation, this parameter. So it is VSG. So as it is quadratic equation, if we expand this, it is ID by Kp and VSG plus 2VSG VTP and plus VTP square. Instead of solving that way, we can directly have a relation by using this equation. So VSG is equal to, so it is VTP plus minus square root of, so it is ID or Kp. By using this relation, we can find VSG. So it will be around, VTP is it is minus, it is 0.60 and plus minus, sorry, no need to take minus here. So, it is 0.60, already we have taken minus here and we got this step. So, it is ID is 0.80 milliampere and Kp conduction parameter is 0.2 milliampere per volt square. So, this milliampere gets cancelled. So, whole square will be up here. So, it is around, I have calculated this. So, I will write. So, it is around VSG is equal to 0.60 plus minus. So, it is 0.8 by 0.2. So, it is whole square. So, we will get here. There are two cases now. One is plus and other is minus. When we are adding and subtracting, as it is quadratic equation, so we can have, so 0.60 and solution for this is plus minus 2 volt VSG. See, now case 1, when we subtract, so VSG is equal to 0.60 minus 2 volts. So, it is around 1.40 volts. So, this is the first case. When we add, so VSG will be 0.60 plus 2 volt. So, it is around 2.60 volt. Okay. But see, it is PMOS, it can be 0.60 plus 2 volt. Okay. Source voltage is positive with respect to gate. So, it can't be negative, sorry, it is negative voltage. So, VSG can't be negative. Okay. One point worth to remember. So, this is the source voltage with respect to gate voltage. Okay. And this voltage can't be negative. See here, it is not negative, it is positive. Okay. So, this is our expected figure. So, 2.60 plus 2.60 is voltage here. So, this voltage is 2.60 volt and it is positive voltage. This voltage should be applied on gate. Okay. So, source is positive means what? Gate is negative. So, minus 2 volt to minus 2.60 is on gate and it is positive at source. Now, we have to find the voltage required to operate transistor in saturation. Okay. That is the condition for transistor to be in saturation. And what is the condition for that? VSD, okay, the voltage on source with respect to drain should be greater than or equal to VSD saturation. Okay. And what is VSD saturation? For NMOS, we have condition to be in saturation. VDS saturation should be greater than VGS minus VTN. Okay. Overdrive voltage should be less than this voltage, VSD saturation, or we can say drain voltage should be greater than VGS minus VTN in case of NMOS. Here VSD should be greater than this voltage. What is VSD saturation voltage? So, it is VSG, we have written here. So, this is the overdrive voltage. So, it is VSG plus VTP. Okay. What is VTP? It is minus. So, it is VSG, we have 2.60 volt minus. So, what is VTP? It is negative. It is 0.60 volt, 0.60 volt. Okay. So, it is around 2 volt. So, VSD should be 2 volt. So, this voltage VSD should be positive 2 volt. Again, source is at positive potential with respect to drain. So, when we maintain 2 volt on drain source with respect to drain, at that time this transistor works in saturation mode, and we have our equation is valid for this condition. Let us solve one more example on basic equations of NMOS and PMOS. It is our third numerical example. What is given? NMOS transistor with VTN is equal to 1 volt and drain current ID is 0.8 milliampere, and when VGS is equal to 3 volt, VDS is 4.5 volt. What we have to find? We have to find drain current. For what condition? For given two conditions. Gate voltage is 2 volt and drain voltage is 4.5 volt. In second condition, gate voltage is 3 volt and drain voltage is 1 volt, and conduction parameter is same for the given MOSFET, 0.249 milliampere per volt square. Okay. So, this numerical example will help us to understand the concept of saturation and non-saturation region. How? Because gate voltage is 2 volt, gate voltage is 3 volt. Gate voltage has increased. In what is done in the second case? Drain voltage is decreased from 4.5 volt to 1 volt. Now, this will help us to understand what is the effect of overdrive voltage on the region of working of transistor. What is overdrive voltage? VGS minus VTN is the overdrive voltage. Okay. When drain voltage with respect to source changes, okay, according to that, region of working of transistor also changes and it affects the value of drain current. Okay. So, we will get the different drain currents. So, let us check for primary condition in which region the transistor is working, then we will apply the given two conditions. Okay. The first condition is here. So, I am labeling this as given condition. What is given condition is VGS is 3 volt and VDS 4.5 volt. Now, how to check the working region of transistor? By using this relation, VDS saturation should be greater than or equal to difference of or overdrive voltage VGS minus VTN. Okay. So, 4.5 volt is given here. So, this 4.5 volt I am going to substitute here 4.5 volt. VGS is 3 volt and VTN is mentioned 1 volt. So, it is around 4.5 volt is greater than 2 volt. Difference of this two is 2 volt. Okay. So, it means, so this is valid. It means transistor is in saturation. Okay. What is our conclusion for given condition? Transistor is in saturation region. Okay. We do not want to find current for this. Okay. We have to find current for this this first condition. Okay. So, this is the primary region of transistor which is given to us, and let us apply the condition 1, condition A. So, VGS is 2 volt and VDS is same 4.5 volt. Now, what will be the working region of transistor? We have to check by using this relation. VDS sat should be greater than VGS minus VTN. So, VGS is 2 volt here and VTN is constant for given NMOS. So, it is 2 minus 1, it is 1 volt, okay, and it is 4.5 volt. It is mentioned here. See this. 4.5 volt. So, this is true. It means transistor is in, we can write here, transistor is in saturation region. Okay. Now, we can apply the current equation when transistor is in saturation. We have DC current ID is equal to Kn VGS minus VTN whole square. So, what is Kn? 0.249 milliampere per whole square, 0.249 milliampere per whole square into VGS is 2 volt here and VTN is 1 volt square. So, it is 0.249 milliampere per whole square. So, it is 2 minus 1 is 1 volt square. See, so no need to take bracket now. So, whole square, so get cancel. So, what is remaining is 0.249 milliampere the drain current. Okay. So, let us calculate for the second condition. Okay, condition B. So, VGS is 3 volt now and VDS is decreased here, VDS is 1 volt. So, what will be the working region of transistor? Again applying this relation, VDS sat is the voltage on drain with respect to source for saturation or when the transistor is in saturation should be greater than overdrive voltage VGS minus VTN. So, it is take given VGS 3 volt minus 1 volt and VDS in this case is this one. It is not 4.5 volt, it is 1 volt. So, it is 1 volt and 3 minus 2 is 2 volt and it is 1 volt. So, this is not true. Okay. So, this is not true. It means the drain voltage is less than saturation voltage. Okay. VDS sat. Therefore, we can say that transistor is in non-saturation region. Transistor is in non-saturation region. Now, this previous equation is not valid. So, this equation is not valid to find the drain current in non-saturation region. So, we have equation for DC drain current when transistor is in non-saturation region. ID is equal to Kn to VGS minus VTN into VDS minus VDS square. So, this is the equation of drain current when transistor is operated in non-saturation region. So, by substituting these values, we can find the value of drain current 0.249 milliampere per volt square. So, it is 2, VGS is 3 volt minus 1 volt into VDS is 1 volt minus 1 volt square. Okay. So, it will be around, so it is 0.249 milliampere per volt square. So, it is 3 minus 1 is 2, 2 into 2 4, 4 minus 1 is 3. So, it is around 3 volt square. So, whole square get cancelled. So, it is around 0.74 something, 0.74 milliampere. Okay. So, what happened here? I will show you by drawing characteristic. I am going to erase this. Okay. See, ID versus VDS, the VI characteristic of NMOS, ID milliampere and it is in volts given, sorry it is not milliampere, or okay our current is in milliampere, fine, we will take milliampere. The first case VGS is 2 volt. Okay, VGS is 2 volt. Say this. What is the transistor state? It is in saturation. So, it is the ID. So, what is the ID we have got? So, it is 0.249. So, it is somewhat more. So, it is 0.249. See, I will draw here. So, approximately I am drawing. So, it is 249 milliampere. Okay, ID. What is VGS? VGS is 2 volt. See, this is the condition in saturation. Now, transistor is a non-saturation region because this voltage, see this. So, this voltage is less than VD set, and this is less than, what is our calculation? So, it is less than 2 volt. It is less than 2 volt. Okay. The VD set should be more than 2 volt, so that it will be in saturation. So, up to this we have the value of drain current. How much it is? 0.74. It is somewhat higher than this one. So, it is 0.74 milliampere. Okay, drain current. I hope you understood.